Hello, good morning. Hope you're doing well today. Okay, so we're going to talk about Newton's second law for rotation, right? And we said the Newton's second law for translation, let's recall what that is F equals ma. Force is equal to mass times acceleration. And in rotation, force had become torque. And we talked about how to calculate torque, right? And mass will become I, that's the rotational inertia, and alpha becomes A become alpha, the angular acceleration. So now what's left in this Newton's second law for rotation is rotational inertia. So today we'll spend some time to discuss what that represents, what it means, and how to calculate it. So since rotational inertia represent basically what mass represent in Newton's second law, we think about, okay, what does that mean? What does it mean to have more mass? The Newton's second law says if you have more mass to achieve certain kind of acceleration, you need more force, right? So same idea here. If an object has more rotational inertia, it will be harder to give it an angular acceleration. So if it was originally at rest, you wanted to make it to rotate, start rotating. The more rotational inertia you have, the harder it is to rotate. Okay, so let's see what kind of variable that affect how hard it is to rotate. Imagine you have a little mass m that's connected by a string that the length of the string is r. You're simply just going to rotate it like this, right? Do you think that if you're having a heavy object, more massive, is it harder to rotate? More massive, it will be harder to rotate, right? But other than just the mass, the string would also, the length of the string will also make a difference. So imagine if you connect the string much longer, you have a much longer string to connect the mass, and you try to rotate that versus a much shorter string. Which one is harder to rotate? The longer string or the shorter string? What do you think? It would be the longer string. Thank you, Jacob. The longer it is, the more rotational inertia it is. So that's intuitive. The I for a point mass is simply defined to be m times r squared. Okay, so here is a short derivation of showing, okay, why is it exactly that format? We can quickly see this by, okay, the kinetic energy, translational kinetic energy is 1/2 mv squared. Now, what about rotational kinetic energy? The rotational kinetic energy, if you change V to omega, it becomes R omega squared. And you can see that for kinetic energy to have a very similar format, right? So from kinetic energy translational, 1/2 mv squared to kinetic energy rotational, they should have the same format. So 1/2 is 1/2. V linear become angular. So M should become I. So you can see that we derived that I is mr squared from this really quick derivation. Okay, so this is how you calculate a rotational inertia if you can view the object as a point. But we know that in real life, we deal with objects of various different shapes. Sometimes it's instead of one point, one ball, you have 3 or 4, right? So you have a few different discrete distribution. Each of them has its own rotational inertia. So in that case, you simply add them up. You sum up everything. So if you have 1, you do m1 r1 squared. You have 2 m2 r2 squared. You have 3, you simply add them all together, right? 1 ball or 2 or 3 or 4. You can simply add them. For a continuous distribution where you cannot simply look at the point object as a point, you have to do the integral. So we said when you do integral, the sum of different m's becomes the integral of little dm, right? So r is measured from the object to the distance from the object to the axis of rotation. It is also, rotational inertia is also called a moment of inertia. So if you see different words, different wording, you should know they all represent I, the same quantity. Let's quickly take a look at a bridge question you have already done. We have, okay, so right now you have this triangle shape made of 3 different identical balls and some rigid rods connecting them, but the rods is massless. So you don't have to think about the rotational inertia of the rods, but simply just the 3 points, the 3 identical balls. So how do we calculate the rotational inertia? Now, relative to different axes of rotation, relative to different axes, the I will change. So for example, if we're calculating it relative to rotating relative to A, so what would that become? Okay, so if we want to calculate what is I relative to A, like we said, we will sum up I is 1, 2, 3, mr squared. This is 1, this is 2, this is 3. 1 is right at the axis of rotation. So the distance r for 1 is 0. Okay, so there's no rotational inertia coming from 1. And you need to do the 2 and 3. So 2 has a mass times the distance for 2. So, okay, from here to here. So let's say half of that distance we call d. If we call this is d, and this distance is 2d, right? So it will be m2d squared for the second ball here. And 3 is exactly the same, right? Same mass, same distance. So you get 4d squared, 4 md squared, that would be 8 md squared. So that is the rotational inertia relative to A. What about the second one relative to B? We will do the same thing. We will sum up all the 3's. Now, all of them has a non-zero distance, right? So 1 has a distance d relative to this axis. So this distance is simply md squared. 2 is 1d. 3 is 1d, right? So md squared. So we get 3 md squared relative to b, which makes sense because think about it. If you rotate this thing relative to the center, you can feel that it's easier to rotate rather than rotating relative to the end. Right? So it makes sense for this to have a smaller I. Last one is IC. IC, because 2 and 3 are both on this axis, there is no distance for 2 and 3. There's no contribution of rotational inertia from 2 and 3. So the only contribution coming from 1, so that's m times the distance from 1 to c, that's 2d squared, that's 4md squared. So you can see IA is the largest, IC is in the middle, and IB is the smallest. So this is how we come up with the answer. So really, what this question is asking us to know is, do we know how to use the definition for rotational inertia, right? This is my definition, our definition for I. So that's for a discrete distribution. Now we are going to look at continuous distribution. Any questions before we move on? So any questions about how to calculate the rotational inertia for discrete distribution? Before we move on to, yeah, go ahead.
So I'm a little confused. So when we're looking at the inertia at point B, for instance, we look at as if point B was our axis of rotation, correct?
Yes. Mm-hmm.
So then if that were the case, then why would, if our axis of rotation was at B, then why would our distance be 1?
Distance d, right? So
Yeah, for part B.
for this, right?
Yeah.
Yes. So we're looking at that distance is defined to be your object to where the axis is. So relative to this axis, this object is at a distance d away. So I do md squared. This object is at another distance d away. So I do another md squared. This third ball is the same distance away from B. So that's another D. So that's md squared. So you add all them up. Did that answer your question?
Yeah. Thank you.
Okay, very good. Thank you for asking that. Okay, now let's move on to talk about, we know how to calculate this. Now let's move on to talk about how to do a continuous distribution. So when something is not a point, they can be all various different shapes. They could be the ring shape or a solid cylinder disc shape. It could be a spherical ball. That can be anything, right? So we're going to show you the formula for various shapes, and we're not going to require you to derive that. You can always, check the table or look it up for these different formulas. But I think it would be good to at least understand qualitatively why these formula make sense. So let's start with a ring. So this is a ring, and you can see the rotation inertia for a ring is the same as a point, simply mr squared. And why is that? So this is a continuous distribution. I can break it up into very little chunks. So a ring is like many little masses all around, right? So if you look at each one of those little mass, they're all at a distance r away from the center. So this point of view is harder to look at. What if I'm drawing a different perspective? So this is like my ring. You see they're all at a distance r away from the center. So if I add up all these different little points, I should get m1 little m, right? R squared little m r squared. But now these m's are a continuous, so you end up having integrate all the masses. They're all at the same distance r squared. So the integral of the mass becomes the total mass of the ring, capital M. So mr squared. So that's why, because all of its mass are at the same distance from the center. So mr squared. That is for the ring. Of course, the equation we're giving you is the equation we're using for the center of axis. That's when you're rotating the ring relative to the center. If you're rotating the ring relative to a different axis, like it's rotating like this, or rotating relative to its end, this formula will change, and we'll get to that later. But this is what you do if your axis is here in the middle. What about a filled disc? So a filled disc is like a ring, but it's not hollow. So everything is filled with mass. So we are saying that the formula to calculate that is the total mass of the disc times radius r squared, and there's a 1/2 in front of it. So if you take a disc and a ring of equal mass, equal radius, so this formula claims it is harder to rotate a ring, and it is easier to rotate a disc of that same amount of mass, same amount of disc, same amount of radius. And does that make sense? That this is 1/2, which is smaller than what it is for a ring. Does that make sense? Does it? Would you expect that 1/2?
Honestly, I would have assumed it would have been a larger than the ring.
Okay, so they're all the same mass. What will happen if you make the disc into into a ring is if I wore all the masses, you don't have more mass. Okay, despite one is hollow, one is filled. I'm not saying they have more mass. It's simply these mass for a ring is all concentrated on the outer side, on the outer rim. For the disc is spread out into the middle. So when you have all the masses further away from the center, will make it easier or harder to rotate when all the masses are further away from the center?
Harder.
Harder, right? So for the ring, all of its masses at a distance r away, whereas for the disk, some of the masses are actually closer to the center. So it will make it overall easier to rotate a disk. And that's why this 1/2 comes into play. So that is qualitatively, I want you to be able to understand why this is 1/2. For a hollow sphere, so you can see a hollow sphere is still smaller than a ring, okay, a 3/2, sorry, 2/3, which also makes sense because for a hollow sphere, you know, some of the masses is at a distance r away, but if you look at other parts, not all of it is at the same distance. Why is that? Because if you say, this is my center of rotation, I'm rotating horizontally, the mass here will have, this is my little distance, right? Here is, this is my distance. So not all the masses is at a distance r away. Some of it is shorter. So it makes sense for this to be smaller, again, smaller than the ring. So 2/3. A solid sphere is a little bit different, is 2/5 for a solid sphere. And you can see solid sphere compared with a hollow should be bigger or smaller. So more of its masses are closer. So it makes sense for this to be smaller than the hollow one, okay? So this is qualitatively how you understand it. But to calculate these, you can use the integral to calculate it. I'm not going to require to know how to derive these formulas, but you need to qualitatively know where it comes from. We can look at more simple situations where to do these integrals. We're not going to look at this the sphere or the disk. We're going to look at a simple situation. Okay, so here I have a rod with a mass m and a length l. So we're trying to set this up for the integral in order for us to calculate the rotational inertia. So to do the integral, okay, what is dm? So we call I is what, r squared dm. This is the definition for a continuous distribution. So to do this integral, we need to figure out, okay, for the rod, everything is simply in one direction. So r simply become x squared dm. So how do I represent dm? Which one of these is correct answer? Okay. So we kind of did this a little bit in the previous classes where we talked about using the idea of a proportion. So think about if you could do that and answer this question. I will go ahead and launch our poll. Feel free if you need to take a minute before you answer. All right. So let's go for another 10 seconds. If you haven't voted already, please wrap up. Okay, all right. Let me go ahead and end this and we'll take a look together. Okay. It does look like we do have agreement on one of the choices. So how do we get that mass in that little section, which is right here, right? So okay, we can use this simple proportion idea that if the entire length L give you a entire mass M, now we're just taking a short distance of dx, how much mass is contained in that little short of length. So that's dm. So our dm is m over L times dx. It looks like C is the correct one. Very good job. Okay, so having set this up, we can calculate what is the rotational inertia for a rod. Again, we're trying to derive a formula for relative to the center, right? So this is my axis of rotation. So you can see that if the entire distance is L, this side is negative L over 2. This is x equals 0. And here is positive L over 2. This is my setup of my coordinates. Okay, so further, let's calculate this. I is equal to dm. So let's plug in dm, m over L dx, x squared, from negative L over 2 to L over 2. Okay, m over L is a constant, right? You don't have to integrate a constant, so you take that out. What you are integrating over is x squared dx. And this is your limits. So this side, this becomes what, 1/3 x cubed to the, with a limit of L over 2, negative L over 2 to L over 2. And so you can see what this become. So this had become 1/3 L over 2, 3 to the power of 3, minus negative L over 2 to 3. And this becomes L third over 8. And there are 2 of these, right? Negative, negative become positive. So 2 of these. Okay, so this had become L to the power of 3 over 4. Now 3 times 4 is 12. So if I put this back with this, you get 1 over 12 m times L squared, because this L cancel one of the L's, so it becomes 1 over 12 L m L squared. So this is for a rod. We had derived one more formula on this list is I for a rod is 1 over 12 m L squared. Okay, so that's one more shape we know from this calculation. Any questions about how we got the result? Any questions here? Looks good. Okay. All right. Okay, now we will do a practice for one more shape. Here you have a disc with a radius r. So from here to here, from here to here, that is r. So this is asking what is the area of a thin ring inside the disc with radius r and then the little thickness, which is dr. You can see extending, the r is a variable extending from the center. So from here to here, it extended an extra depth width of dr. Okay, so we'll be able to find out the area of that little ring. So this will help pave the way to calculate the rotational inertia for the entire disk. So first, let's go ahead and try to answer this question. I want to remind you, there is sort of a shortcut to this question. You might wonder, well, that's a weird shape. I don't know how to calculate it. But think about, okay, we're asking for an area. You needed to have this correct dimension, right? What should the correct dimension for an area? That will help you get rid of some of the obvious wrong answers. All right, just 10 more seconds. Let's wrap up with our votes. Okay, all right, let's go ahead and end the poll. We'll take a look at this together. Okay, now I noticed quite a lot we voted for A. Pi r squared looks familiar, right? So that makes sense why you want to vote for that one. So we talked about what dimension the area has to be. So area has to have what dimension? What do you think? A length dimension? Length squared? Length cubed?
Length squared.
Length squared, very good. Has to be length squared. So I think what might be tripping people off is, well, what about little dr? Does that give you a dimension of length, or does that give you a dimension of 1?
Doesn't dr give another dimension of length?
Yeah, doesn't dr give you dimension? It does. Very good, Grant. And thank you, Juan, for contributing as well. It does. dr give you a dimension. It's a small distance, but it's still a distance. So somehow this one give you a length cubed. This length square, length cubed. So that's not going to give you the correct dimension for an area. Right, this one as well, it's going to be wrong. It's give you a length fourth. Now the only correct dimension is B. So we can rule out the incorrect ones, but now how do you get the 2 pi r times dr? So I know this thing range looks weird, But let's think about this. Let's say you take a scissor and you cut it, and then you cut it and you expand it. What do you get? You get something like this. Okay, very good. So if I think about cutting it and expanding it, it looks like a long rectangle, a very skinny rectangle. What are the two sides of the rectangle? What about the little width? What is this?
ER,
dr. And what about this?
R, lowercase.
So this is, I have expanded this.
It's 2 pi r because that's the not the diameter, but the circumference of the circle.
Right, yes, that's the 2 pi r, very good. So by doing this little trick, you can see the area is 2 pi r dr. Excuse me. Okay, so why we're trying to do this setup? We wanted to be able to show the derivation of this particular shape. Let's do that. Okay, so we said I is r squared dm. This is our generic formula. For dm of this thin ring is the area we have just derived, right? So that tells me what is the dm? dm will be the mass density times this area. And again, I can get that from the proportion, thinking for the entire ring, it has mass m of area pi r squared. Well, that's the entire ring, right, with this area. But I'm taking a small chunk with this area, and what is the little mass contained in that area. So dm is calculated to be m over pi r squared times 2 pi r dr. Get rid of my pi, becomes 2m over r squared r dr. So that's the little area contained in that very thin ring. So to put this back to calculation, you get 2m over r squared, r dr times r squared, so r cubed dr. And what are my integration limits? So for r is from 0 to what? From all the way from the center to the edge, okay, so 0 to r. Okay, so 2m over r squared is constant, and this becomes 1/4 r fourth 0 to r, so that becomes r squared. You can see this becomes r squared, so r fourth, and that is 1/2 m r squared. So this is what we had just see previously, rotational inertia for a disk. And a cylinder is really just a disk, right? Higher or shorter. Excuse me. So this is all the things we have seen so far. A ring, a disk, hollow sphere, solid sphere, and the rod. We derived this one ourselves. We derived this one ourselves. But I would say we're not going to expect you to know the derivation on exams. You can always look up these different formulas. But I encourage you to understand where these formulas come from and somehow have some of the frequently used ones that memorized, so it's easier. Like this one, we should probably know by heart. This one we should know. This one we should know by heart. Okay. One last thing is, what if your axis is not through the center? Through the center should make it easy to rotate, but your axis is further away, it's going to be harder to rotate. So for example, So axis is parallel to the center. We have a theorem we can use to calculate the new rotational inertia. So we call that parallel axis theorem. The new rotational inertia is whatever it is relative to the center of the mass plus the mass of the object times the distance between your new axis and your center of the mass axis. So we can try to use this in the following questions. So for example, you have the different rods, one relative to the center, one relative to the end. Which one has a larger moment of inertia? Well, I already know you guys know which one is larger because the center of the mass is always the shortest one, the smallest one. So this one will be larger. But how do we calculate it? We're going to use this equation to help us calculate it, okay? So relative to the center is 1/12. This is what we just derived, or you can look it up. Relative to 1 at the end is whatever is relative to the center plus the mass times the distance. So the distance of the new axis relative to the center of the mass axis, you can see it's the half of the length of the rod. So that is D is going to be L/2 squared. So adding them together, you get 1/3 ml squared. So this is bigger, of course, than I relative to the center of the mass. So when you change your axis away from the center of the mass, you are always going to get a rotational inertia bigger, which make it harder to rotate. Because of the parallel axis theorem, right? You're always adding something, not zero. Okay, so the answer to this is IE is larger than IC. Of course, fine, exactly. We know what IE is and we know what IC is. Okay, one more question. So this one you have done yourself. You're comparing two masses, 3m and 1m. They're connected by a rod. Again, the rod is massless, so you don't have to worry about the rotational inertia of the rod, just the two balls. Let's say we choose different axes. We choose to rotate it relative to A, relative to B, or relative to C. Now, how do you compare? And which one is biggest, which one is the smallest? So there are two ways to do this. One way is, well, let's just calculate each one of them and compare which one is the smallest, right? That's the first method. So let's look at the first method. If we calculate each one of them, we have talked about this. This is a two discrete distribution. You simply add them up. Relative to axis A, you can see 3m sitting on axis A. You don't have to worry about its center of mass. So it's really just B, the other mass. So it's going to be m times the distance from here to the axis is L, so ml squared. So that is IA. Next one is IB. Relative to here, both of them will have a distance. The 3m have L/4 distance. The 1m has a 3/4 of L distance, right? So you simply plug it in and calculate it. Last one is through the middle. So each of them have an L/2 distance. You calculate it and you realize, oh, B is the smallest. So that is one method. The second method has to do with what we just talked about. This is method 2. We know that, well, you want to find the smallest. I know that the rotational inertia relative to its center of mass is always the smallest. Any other axis, right? Any other axis is this rotational inertia plus md squared. So this is always the smallest. So let's just see where the center of the mass is. Is it at A, point A? at point P or at point C. So do you guys still remember how to find the center of the mass? So given this distribution, X center of the mass is, so how do I calculate this? Do you still recall?
Wasn't it finding the center of the rod or our object in general?
Right, we call this equation MIXI over total M. This equation. So this is
Yeah.
the location of the center of the mass. Is the average position of all the masses, right? So each of the mass has a different location and we average over. So let's do this. 3M is, if we call this 0, right, is at location 0. 1M is at a location L. And they have total of 4M. Right? 3M plus 1M. So where is the center of the mass? The center of mass is ML over 4M is at L over 4. So this is where the center of the mass of the two object distribution is. So it looks like a center of mass is right here where B is. So of course, if you rotate relative to B, it's going to give you the smallest rotational inertia. So you could also use this method and right away you know B will be the smallest without having to calculate each one of them, right? So that's the second method utilizing our parallel axis theorem, knowing that the center mass is always the smallest one. All right, any questions so far about parallel axis theorem? Any questions so far? Okay, if not, let's move on to take a look at this. So what about the kinetic energy? Soon enough, we will start looking at the rotational kinetic energy of different objects, and we'll use that to solve more problems. So to do that, we will be able to, we will have to use the definition for the kinetic energy of rotation, which is 1/2 I omega squared, remember? Okay, so you want to see a previous slide, which is this one. Maybe this one. Okay, no problem. So we have various different shapes. They all have the same mass, same radius. They all rotate relative to the center with the same angular velocity. Which one has the largest kinetic energy? So let's take a moment and go ahead and we're voting on this one. All right, so let's go for 10 more seconds. If you haven't voted already, please do so. All right. Okay, I'm gonna go ahead and end this. We'll take a look at this together. Okay, so now we're comparing which one has the largest kinetic energy if they were all rotating with the same omega. So you can see that if omega is the same, it's really just comparing which one has the largest rotational inertia. Okay, so if they're all having the same mass, same radius, right? Which one has the largest I from this list?
The ring.
The ring, yeah, everything else is have a constant that's smaller than 1. So ring is the largest. The largest is simply just the ring. So if you're able to get the ring to rotate as fast as the other ones, which means you have to give the ring more energy. Right? It's harder to rotate. So that is a ring is the largest. Okay, so that's choice B is correct. Very similar question to that is this is a bridge question. With the ring, you can even rotate it differently. You can rotate relative to the center of axis, okay, which all of the masses is at a radius r away, okay. However, if you do something different, you rotate the ring 90 degrees and you rotate it relative to this axis. So what happens there? Do you think that will have the same kinetic energy or larger or smaller? So given the kinetic energy is 1/2 I omega squared, they're all rotating with the same omega. So this is the question is, what is I in case 1? How does that compare with I in case 2? Are they equal? Or I1 bigger or I2 bigger? What do you think? Case 2, they'll have less. And why is that, Jacob?
Because some of the mass lies on the center of axis, extending out towards the radius.
Very good. Some of the mass is having a same radius r, but some of the mass you can see have a much shorter radius. Right? The mass over here has a 0 radius as the mass over there. Very good, very good. So that makes case 2 will actually have a smaller rotation. So like if you have a little ring, rotating it this way versus rotating it this way, this is case 2. Case 2 will be easier. It has a smaller I, require less energy. The most energy will be case 1. Okay, excellent. So that's all we have for today. Next week, we will be able to put this together to help us solve Newton's second law problems for rotation. Have a good weekend, everyone. I will see you next time.
Professor, thank you. Have a good weekend.
Thank you, you too. Bye-bye.